This work presents adaptive complexity model predictive control, a new approach for the control of dynamical systems which leverages online model reductions to solve a wide range of challenging problems. Adaptive complexity model predictive control is a solution to a fundamental issue in model-based control, the trade-off between simple and complex approaches for solving problems. Simple models have been shown to be very robust and efficient, particularly when performing tasks requiring reactive behaviors. In the domain of legged robotics, this could include rapid accelerations or responding to unknown disturbances. However, for tasks that require more model fidelity, such as stepping or leaping over obstacles, the assumptions contained in these simple models often break down, leading to infeasible or suboptimal behavior. Approaches that use more accurate but computationally intensive models can show remarkable flexibility to solve a wide range of these tasks quite intelligently, but these same approaches can often struggle to demonstrate the same reactivity as their simpler counterparts, and even when they do, they often consume large amounts of computational resources. The solution to this trade-off is to adapt the model according to the needs of the problem. This solution is inspired by a diverse range of prior work from behavioral economics to biomechanics, which explore the utility of complementary fast and slow processes which together exhibit remarkable performance. The key contribution of this work is combining this concept with a model predictive control framework. In this framework, prior predictions are processed to identify segments in time where the model can be safely simplified. These simplifications then yield smaller optimal control problems, which can be solved more efficiently. It can be shown that when the simplified regions are identified by checking some common template and anchor relations, provable stability of the system is maintained. We measure the efficacy of adaptive complexity MPC in 3 different experiments performed on a simulated quadrupedal robot, where the simple model ignores leg kinematics while the complex model captures their constraints and approximates their dynamics. For each experiment, we compare our adaptive approach to 3 fixed complexity configurations, one that only uses a simple model, one that only uses a complex model, and one that uses a fixed mixture of the 2. In the first experiment, the robot is suddenly provided with a task to accelerate and decelerate as quickly as possible over a short distance. This task rewards reactive systems with low solve times, which can quickly respond to the aggressive input. The simple configuration thus performs the best, with a 2-fold increase in top speed over complex. Though not as fast as simple, the adaptive approach still shows a 60% improvement over complex due to its ability to simplify the problem when admissible. In the second experiment, the robot is tasked with walking over a hip height step, which requires precisely navigating kinematic constraints. Due to their knowledge of these constraints, the complex, mixed, and adaptive configurations can all take corrective actions by adjusting the body position and foot trajectories to climb the step, while the simple configuration stumbles. This is reflected in the lower overall control effort for configurations with more constraint reasoning. The figure on the right shows the percentage of the prediction horizon, which has been simplified over time. The curve for the adaptive configuration, shown in green, indicates that for much of the behavior, the simple model can be deployed to conserve resources, and that complexity need only be retained to navigate kinematic constraints such as joint velocity limits or terrain clearance when swinging the feet over the step. In the third experiment, the robot is tasked with leaping over a body length gap, which requires precisely navigating both kinematic and dynamic constraints. Only the complex and adaptive configurations can clear the gap. Their ability to reason about joint constraints near the end of the prediction horizon allows them to take early corrective action, in this case lowering the body to increase the leaping stance time. However, only the adaptive configuration can then remove this complexity to conserve resources, resulting in a 40% reduction in average solve times. In summary, adaptive complexity model predictive control is a new approach to controlling dynamical systems, which retains the benefits of complexity when needed and sheds its drawbacks where admissible to improve performance. One limitation of adaptive complexity MPC is that it is still subject to the numerical structure of the complex system, which can be quite brittle. Methods that improve robustness to these effects, such as constraint relaxation, intelligent warm starting, or robust MPC methods would benefit this work. To retain certain theoretical properties, our adaptive configuration was quite conservative when choosing to simplify the model. It is possible that more optimistic approaches would enable more considerable performance improvements. Lastly, recent works in MPC for legged systems have shown impressive performance using structure exploiting solvers to enable whole body planning online. Combining the adaptive approach here with those advances could potentially enable even more precise and reactive behaviors.